In this video, I aim to highlight the importance of polymers in F1 and specifically how this relates to the safety of drivers. Formula One cars are an amazing piece of technology and reach speeds unimaginable to most, but achieving speeds like these come with consequences, like what happens if a car crashes. This is unfortunately inevitable, so how are the cars designed to minimise the risks associated with these high-speed crashes? To start with, let's look at one of the most dangerous crashes recently. Romain Grosjean's crash on the opening lap in Bahrain. To this day, I am still in awe of how he managed to survive, let alone only having minor injuries. Keep your eyes on the bottom right of the screen. He struck the triple guardrail barrier at 119 miles per hour with a 67G impact and was in the fire for 27 seconds before escaping, with only burnt hands. FIA investigations concluded that the driver's safety equipment, including the crash helmet, head and neck support and safety harness, as well as the survival cell, the seat, the headrest and the halo, were found to have performed as expected to protect Grosjean. So what's the design behind this equipment that essentially saved his life? The answer to this is quite simply polymers. Polymers saved his life. These included carbon fibre, Xylon, polycarbonate, high-density foam, Kevlar, rubber and Nomex. Carbon fibre makes up 85% of the volume of an F1 car. So let's look at what it is and why it's so useful in Formula One. This very recognisable weaving pattern is what makes it such a desirable polymer. The interlocking of fibres crossing perpendicular to each other allows it to be so stiff, rigid and have a high tensile strength, making it perfect for F1 cars. Carbon fibre is made of a carbon-based polymer, most commonly polyacrylonitrile, which is made via free radical polymerization of its monomer acrylonitrile. Many of these monomers join together to form a long polymer chain. This is how manufacturing of carbon fibre begins. But how do we get from acrylonitrile to polyacrylonitrile? This is done by free radical polymerization, the first step being initiation. This is followed by propagation and then termination. Like the name suggests, we need an initiator, something to kick-start the chain reaction, and in this case it's benzoyl peroxide. The single oxygen bond homolytically breaks. This forms two radicals. This radical moves further down the chain to the benzene ring. Carbon dioxide and the benzene radical are the products. This benzene radical is what starts the reaction. Now we have an initiator, propagation can begin. The phenyl radical reacts with acrylonitrile to form 2-phenyl propanenitrile radical. Along comes another monomer and the same thing happens again. As this product is a radical, it can react again with another monomer, and this continues until a very long chain is formed. And finally, termination, when two of these long polymer chains react together to form one very long polymer chain. We have now formed polyacrylonitrile, our final product. So how do we go from polyacrylonitrile to carbon fibre? This is a multi-step process, the first being dehydrogenation. The backbone is now alternating single and double carbon bonds. Next is cyclization, where one of the pairs of electrons in the carbon-nitrogen triple bond is transferred to a neighbouring carbon. We now have a chain of interconnecting rings. Now we oxidize it. This, as you can see by the brackets shown, has multiple different possible products. Finally is carbonization, where these polymer chains react with other polymer chains to form the final fibre thread. You'll be pleased to know that's it. We now have our polyacrylonitrile based carbon fibre thread. Multiple of these threads are then woven together, which forms the big sheet carbon fibre that you see on F1 cars. So now we know how carbon fibre is made. What are its properties that makes it so beneficial to keeping the F1 drivers safe? Carbon fibre has incredibly low thermal expansion. So going back to Grosjean's crash, the chassis of the car keeps its structure and doesn't deform. It also has very good mechanical strength. This means that it can be exerted to higher forces and it will still retain its original shape. However, in Grosjean's crash, it was such an extreme force at 67 G that this was not the case and it did snap. However, by its snapping, it allowed it to take a lot of the impact without it being transferred to the driver. As mentioned earlier in the video, Kevlar is another synthetic polymer used in fuel tanks. This bulletproof material is 8 times stronger than steel. A diamine and a diacid chloride react together. This is a condensation reaction. The para-amide links is what gives Kevlar its immense strength. The amide bonds allow the chains to interlink. The pink lines here show the hydrogen bonding, and as you can see, there's loads of it. The next polymer is Nomex, which has a very similar structure to Kevlar, but the slight difference results in the properties being very different. Again, like Kevlar, it's formed from an amine and an acid chloride. As you may have spotted, the functional groups are meta to each other on the benzene ring. These meta-amide links are not as strong as the para-amide links in Kevlar. This makes Nomex much less strong than Kevlar. However, it means it's flame resistant, unlike Kevlar, which is only heat resistant, making it perfect for fire retardant clothing. So we've looked at carbon fibre in the chassis of the car, Kevlar in the fuel tanks, and Nomex in the clothing. All of these contributed to saving Grosjean's life despite the huge crash. This shows how crucial chemistry and synthetic polymers are in F1 cars.